Now this one I think is where it's contentious. Sometimes it works, sometimes it doesn't work. Not all the tricks I'm teaching you work all the time, and there will always be interplay or interactions between the different tricks. Okay, so like in this case, for example, in the network itself set up with a bottleneck, here I have an inner product layer as my final LC layer on the final one, because I don't have a thresholding on the scaling layer, right? So my scaling layer is not thresholded. That means it's not a 10H. It's just scale, all right? Which means you can vary quite a bit even with the scaling, right, done. And I need to have the inner product or the LC layer to compensate for that. Now, when I use, in the second example, using the squared inputs, I want to start this shortly, this will change. So this is what I mean by interactions between these different tricks. You need to know what you're doing, okay? So it's a very simple thing. The first equation is just your normal, your normal input, right? So you've got some a dot product, and then you get a saturator, and that's your Y for your neurons, right? But sometimes when you have an X squared, that can give you the benefits of both perceptrons and more different networks called the RBF, or radial basis functions networks. Okay, this trick doesn't work all the time, and it's fussy to use in my experience, but I'll teach it to you anyway, so you can just play around with it also. Okay, and the idea is this, that perceptrons have got some set of benefits. They are less problematic when it comes to a large dimensional input. I'm saying large, but let's say around 100, but they are slower to train. RBF networks are fussier to train because they need smaller dimensional inputs, but they train well and quickly. Okay, so the idea is that if we can square the inputs before we feed our network, we can perhaps gain some or see some benefits. Okay, that's the theory at least. Let's try, or hypothesis, I would say. I wouldn't call it a theory, I'll call it a hypothesis, because none of this stuff is really proven mathematically. Okay, it's more experiential. Okay, so let's go back here. So I've got my dimensional reduction subnet, and this time I've commented out the final LC layer, and I'll explain why shortly. And that's because here I've changed my main network. I first scale, and then I add the squares to the squaring function here before I go to the bottleneck, right? So my squaring function, what I've chosen to do is to use the 10H to actually flatten it before I feed it into the main network. Before I feed it into the bottle network. If you do that, if this is already 10H, then you don't need the inner product anymore. But if this were not 10H, like that, then obviously you need to put this in because you want this to scale properly, because otherwise this is already 10H. It cannot match something that is not being flattened. Okay, so I'm doing the reverse, which is this, and I'm flattening it out here. Okay, and I'm obviously, as usual, reporting the loss separately as well. So now the losses. Okay, so this looks terrible, and it probably is. What it tells you is that, okay, this is not a... Okay, so what's happening here is this, okay? The stuff that you see down here, the blues down here, they are being overtrained because you can see the losses are very small, 0.29. So far, one of our better losses is 0.45, okay? And for each of these guys, you're getting all these upward test arrows because it's obviously overtrained, so you get a symmetric, flip up by the test losses. But for a few around this range, you're getting some training, and you're getting that kind of balance between training and learning. Now, what you notice immediately is that, and of course, the reconstruction is not too bad. Okay, it's doing pretty well. But the errors are quite big. Look at this error out here. So this is the blue is the training error, and the red is the test error. Okay, and early stopping is cropping it off quite early at just 850 cycles, iterations. all right? And the error here is pretty large, 0.54, okay, which is even worse than what we had done before. But if we look at the predictions, we come to understand why the error is big. What happens is this: when you have these squares put in, what you'll notice is that the predictions will start to fluctuate. You get oscillations, and you do get improvement with the lags, but at the same time you get these oscillations, and the oscillations are what cause the training losses, so the test losses to go up. Okay, so this is more of an advanced technique, and you need to be very careful using it, and you need to play around with it to get the right values. Also, what I noticed also using this technique is that the optimum numbers for the config, etc., changes. So previously we had 4 and 0.2, but when you introduce the squares, the bottleneck size that you can take, it's happy with, is much lower. Okay, so we have 30. Previously we had 33 and we reduced it to below 10, and now we've got 33 and it's just 15. Okay, and I needed to use more aggressive dropouts as well, because these were becoming it's a bigger vector. Sorry, not because it's a bigger vector, because that was necessary for the thing to work. Okay, all right. I think I'll stop here. Any questions?
Maybe let's return to one of the questions that was asked.
Yep.
Whether can you explain a bit more about the persistence that you were talking about through the talk? Can you share a bit more on the persistence, the definition, or maybe even the details a bit more?
Okay, so persistence is just a simple, trivial forecast. It's a benchmark, a brainless benchmark. Okay. So what it's a forecast. So let's say, for example, you got let's talk about, I'm a stockbroker, okay, and let's say you're my client, and Ku says to me, Arnold, can you give me a forecast for the stock? Let's say Google stock, I don't know, 1 month from now. Okay, I said sure. The answer is I check the value today, and I tell you today. So what's the price of Google stock today? Let's say it's $100 or $200 or $1,000, whatever it is, right? I say it's $1,000, right? And that's my forecast. No matter what you ask me, I say it's the current value. So tomorrow you ask me again, I will say it's tomorrow's value, right?
Okay.
So that's a persistence forecast. So it's very much used in a lot of forecasting because it's simple. Okay. Number two, it is actually hard to beat for short lead times. So, for example, this is true for things like temperature. For temperature forecast, let's say we're talking about what is the forecast for temperature for tomorrow, and I give you today's value, you'd find that very hard to beat. Very hard to beat indeed. Okay. And if you did, it means that your model is really doing something behind the scenes which you're not seeing. And short lead times are important for things like dynamic demand pricing or demand forecasting. Like, let's say you're in Grab or Gojek, I guess. You're trying to dynamically price your rides, right? And therefore, you need to actually forecast the demands for your rides based on historical data plus current conditions, etc. Right? So the pricing time horizon is very short. Usually it's about 30 minutes or 15 minutes, maybe about 30 minutes ahead of time. Okay, so the forecast 30 minutes ahead of time, persistence is usually quite hard to beat. Okay, it's very noisy for these kinds of things, and persistence is not a bad gauge. Of course, if the time horizon shifts, let's say to tomorrow, for demand forecasting, something that's very, very fluctuating, then of course persistence will be very easy to beat.